So in this work, we consider tasks where a bimanual robot must move an object between two stable tabletop configurations. And we assume that we are provided with a set of primitive manipulation skills, along with a high-level sequence of the skills that can be used to complete the task. In particular, we utilize primitive skills which take in parameter values and return low-level motions. The parameters are the initial world frame end effector pose and a relative rigid body transformation. All our skills assume that objects are rigid and that the robot will maintain sticking contact with the object. So with these primitives in mind, the problem is then to find an appropriate sequence of intermediate transformations and contact poses so that the low-level motions will bring the object to the overall goal. And the current solution techniques for this type of problem typically assume that the geometry and pose of the object is known. However, the challenging aspect of our setup is the assumption that we do not have access to a 3D model or pose of the manipulated object. So to obtain this plan, while operating directly in the sensor space of the system, we choose to represent objects by a raw segmented point cloud and train neural networks to map point cloud observations to a distribution over the primitive parameters. And because the primitives assume sticking contact, we can directly apply the sampled transformation to the observed point cloud, which enables us to imagine the point cloud observation that would result after executing a skill. So then the transformed point cloud from the first step can be used as the input when we sample parameter values at the next step. And this process can repeat iteratively while checking for feasibility and searching for an overall sequence of transformations that reaches the goal. So for our system, we collect training data in simulation by executing the skills on many differently sized cuboids. And we then train a conditional variational autoencoder, where an encoder learns to map the data to a conditional latent distribution, which is constrained to match some prior. And a decoder is trained to map the point cloud and sampled latents back to reconstruct the parameter values. And then during planning, we sample many values of the latent variable from the prior and use the trained decoder to obtain a corresponding set of candidates for end effector poses and relative transformations. However, when directly sampling relative transformations, it's very possible that the transforms are sampled that are feasible for the robot, but which are unreachable for the object. For instance, the transformation could lead to the imagined point cloud penetrating the table or floating in air or contacting the table in some unstable configuration. So instead of directly sampling transformations, we propose to represent SE3 subgoals with a binary segmentation mask that the neural network must predict, which encodes which points in the point cloud should end up in contact with the table. So we can then use these mask points along with the table point cloud to solve for a transformation that will bring the mask points to be in contact with the table. And our experiments, which are designed to evaluate how well the system can sample its own subgoals and reach them, validate that this choice of SE3 subgoal representation leads to improved performance. We also compare our learned generative models with manually designed baseline samplers in a multi-step planning with cuboids that were not seen during training. And the results show that our learned models provide a large benefit in fixed budget planning success rate. We also have some qualitative results that indicate that we obtain some generalization to different classes of geometry and that the models trained in simulation will successfully transfer to the real world. So in summary, our method enables sequencing primitive skills without requiring a 3D object mesh. And by using primitives parameterized by relative transformations and which assume sticking contact, we enable reliable forward search directly using point clouds. And our results show that this approach offers planning efficiency benefits and has the potential to enable generalization toward multi-step manipulation with more diverse and complex objects.